Professor Ravi Kumar sir.
Yes, madam.
Sir, shall we start the program, sir?
Sure, madam.
Thank you, sir. Respected resource person of the day, Captain Dr. S. Ravi Kumar sir, Professor in Mathematics, Andhra University, Dr. G. Teresama Gade, the correspondent, Dr. Shaini KP, the principal of JMJ College, and FDP participants. Good morning, everyone. I, Dr. Uma Maheshwari, convener of the FDP, head of the Department of Mathematics, extend my cordial welcome to today's resource person, Dr. S. Ravi Kumar sir, and fabulous welcome to all the participants of FDP on behalf of the Departments of Mathematics and Physics, JMJ College for Women, Tenali. Dean William R. Inge once said, "The aim of education is the knowledge, not of fact, but of values." It is an occasion like this we get opportunities to test our knowledge and understanding. We look forward to get an exposure about what the best of the brains thinks about this very dynamic FDP on effective pedagogy for science. Once again, I extend a warm welcome to all. Mr. Murali, are you ready for prayer?
Yes, ma'am.
Please start the prayer. Prayer should be the key of the day and the lock of the night, says George Herbert. May I call upon Mr. Murali, the computer operator, to display the sound.
Lord, we come to worship you. Hallelujah. Thank you, God.
Thank you, Mr. Murali, for filling the ambience with the celestic music of God. Respected participants, I now invite Mrs. B. Bharati, the member of the organizing committee, Department of Mathematics, to introduce today's resource person, Captain Dr. S. Ravi Kumar sir, who is going to deliver a speech on the topic normal ADLs, relatively dually normal ADL.
Respected galaxy of individuals, respected galaxy of intellectuals,
I, Bharati, lecturer in mathematics, JMJ College for Women, Tenali, feel elated to introduce our today's eminent resource person, Captain Dr. S. Ravikumar Sir, Professor in Mathematics, Andhra University College of Science and Technology, Andhra University, Visakhapatnam. Sir has truly set a benchmark for multi-hyphenated achievements, a renowned motivator and facilitator, and stands tall amidst the glare of educationists. Sar obtained his doctorate degree on the thesis Normal Almost Distributive Lattices from Andhra University in the year 2010. He published 8 international journals and completed his minor research project on a study on normal almost distributive lattices in the year 2016. He authored several books, namely Telanalysis, Linear Algebra, Differential Equations from Andhra University School of Distance Education. He has 30 years of teaching experience. Under his able guidance, students able to complete their MPhil and PhD degrees. Sir, it gives me great pleasure to have you with us as we have been eagerly awaiting from you. Once again, I welcome you, sir. Now, the floor is yours, sir.
Thank you, Bharti Garu. And thanks to the management of JMJ College and for giving this opportunity to present my research work to the youngsters who are working on particularly lattice theory and who wants to do some work on algebra. It's a privilege to me to express my the research articles, whatever I have submitted. And among those, I have chosen a best one, which gave me a tremendous satisfaction for me in doing my research work, and particularly in normal distributive lattices. You might have, those who are working on algebra and lattice theory might have understood the definitions of distributive lattices, Boolean algebra, and many certain things. And during your graduation, you might have gone through abstract algebra. And there we have studied about ring theory, and with the interest in providing a relation between the rings and lattice theory, the concept of almost distributive lattice was came into existing. And this is established in the year 1980 by my teacher, Professor G.C. Rao Garu, on the name of almost distributive lattices. And the concept of almost lattices was established by Professor G.C. Rao Garu under the noble guidance of Professor U.M. Swami Garu in Andhra University itself. And if you observe these concepts, particularly almost distributive lattices, you could see almost all the concepts which are related to distributive lattices are coming out only from the Department of Mathematics. It's a great opportunity for the youngsters to work on lattices and basing on the distributive lattice with a minimal element. And in a distributive lattices, we might have gone through what is a minimal element and what is a maximal element. And when you have a bounded distributive lattice, it becomes if it is a complemented bounded distributive lattice, you will understand that it becomes a Boolean algebra. Now, my concept is with the help of certain properties, we will able to develop many concepts, whatever satisfying in a distributive lattice can be developed with the help of a almost distributive lattice. So let us see how we can establish the concept of normal almost distributive lattice with the help of minimal properties. Now, dear colleagues, can you hear? Is my voice audible to you?
Yes, sir.
Yeah, thank you. And this is the work I'm going to present now, normal almost distributive lattices. And in normal almost distributive lattices, we have a concept known as relatively dually normal ideal. And just to know about these things, we should know what is an almost distributive lattice and what is a normal almost distributive lattice. And we have defined there in some dually normal ideals. And in dually normal ideals, with the help of relatively normal ideals, we have gone through, and also we will discuss about relative dual annihilators and relatively dually normalized. Just brief introduction I would like to give on these 6 topics. And before that, you will see what is the basic concept which made us to introduce the concept of almost distributive lattice. This is the concept, historical background of our almost distributive lattice. For giving generalization to ring theoretic and lattice theoretic concepts, this concept has existed with an idea of a common abstraction to most of the existing ring theoretic and lattice theoretic generalization of a Boolean algebra. The almost distributive lattice was introduced by my teacher. I already told you, this is by Professor G.C. Rao Garu under the noble guidance of Professor U.M. Swami. The class of almost distributive lattices includes almost all the existing ring theoretic generalization of a Boolean algebra. And we can see P rings, regular rings, biregular rings, and many of such on one hand, and the class of distributive lattices on the other hand. These are the topics we are going to cover in our in this particular session. And in today's seminar, these are the topics we'll be going to do. And let me introduce the almost distributive lattice. See, if you look into this definition, we can see only 5 properties. With these 5 axioms, we are able to develop almost all the existing developments of our distributive lattice. Whatever we have done there, will be able to find in our almost distributive lattice. Now, let us see. These are the 2 distributive lattices we have. And these 2, if you observe the first 2, they are nothing but the distributive properties which you have studied in a distributive lattice, and the 3 absorption laws we have. With these 5 conditions, the almost distributive lattices will going to act a powerful tool in developing the concepts of a distributive lattice. And we can see how when we can convert an almost distributive, an ideal to a distributive lattice. And these are the examples we have. Every distributive lattice is an almost distributive lattice, and to develop certain concepts in almost distributive lattices, we have taken this particular definition, and we are introduced a 0 element in the distributive lattice, and we call it as the least element of that almost distributive lattice, which satisfies the property 0 meet A is equal to 0 for all A in capital R. And this algebra then from now onwards will be known as an ideal with 0. And we can see in 1.3 any non-empty set, whatever non-empty set you have, by definition in such a way, by join and meet, we can see every non-empty set can be an almost distributive lattice. If the distributive lattice, an almost distributive lattice defined in this particular manner is known as discrete ideal. Now, if you see the other property, partial ordering, if you define a relation less than or equal to between A and B of any elements of an ideal, by A is equal to A meet B and B is equal to A join B, we could see that particular ideal becomes a partial ordering. These are some properties which are included in the definition of a distributive lattice. But we see with the help of those 5 properties, we are able to develop all the properties which we can see in our distributive lattice. So this is the major advantage of an almost studying an almost distributive lattice. If you see whenever A join B is equal to A, we will have A meet B equal to B, and A join B is equal to A. Since it is a partial ordering with respect to the operation less than or equal to, we could see whenever A less than or equal to B, we get A join B is equal to B join A. And actually, in distributive lattices, this exists because there we will have commutativity with respect to join and with respect to meet. But whereas in normally distributed lattice, we don't find this. So that is the advantage. Though we are not having the duality principle in almost distributive lattice, we could see these things can be developed by having this partial ordering with the ordering less than or equal to. That is major advantage of this almost distributive lattice. There we can see the meet is associative in R. That means A meet B meet C is equal to A meet B meet C. That is another advantage we are really having. And these are some other properties we can see. Whenever A meet A is equal to A, you will have A join A is also equivalent to A you will have. And see, this made us, if one of these properties have in our ADL, and that ADL becomes our distributive lattice. See, what are the one of the four properties? If A join B is equal, that means join commutative exists in any ADL. See that ADL becomes a distributive lattice. And if you see the third property, if meet commutative exists in an ADL, we will have that ADL becomes a distributive lattice. And if you see the last property, actually we don't have this particular distributive property in an ADL. But if you have this particular property in an ADL, then that ADL becomes a distributive lattice. That means what? We will be having more generalized having definition in ADL, which can make us to get all the properties of a distributive lattice. And see, if you compare with a distributive lattice with bounded distributive lattice, there we can see a greatest element and a least element. Whereas in our almost distributive lattice, we don't have that opportunity. And we have started whatever we are dealing, what are the topics we are discussing here in my paper, we will be dealing with an ADL with a zero element. And that ADL may have many maximal elements. And this is the definition we have provided for a maximal element. An element M in R is maximal if whenever M is less than or equal to A, we will have M is equal to A. This is similar to the definition of maximal elements in a distributive lattice. And these are the properties we are having. If M is maximal in an ADL, then M join A becomes a maximal element, and M meet A is equal to A. And of course, the element A join B becomes a maximal element. So that is a beautiful theorem we have proved while doing some work in almost distributive lattice. And the major thing, if you want to define a normal our concept to define a normal distributive lattice, we should see it involves ideals and filters which helped us in developing a normal almost distributive lattice. And this is the definition we have. A, B are any two elements of any non-empty subset I of an ADL R, and if these two properties holds, A join B should be an element of I, and if we take an element A from the non-empty set A and X is any element of R, we will have A meet X belongs to A. If these two conditions hold, we say that that non-empty set becomes an ideal. And similarly, we have defined a filter in an ADL. See how we have defined A meet B should be an element of F, and A belongs to F, and X is any element of R. We will have X join A belongs to F. Similar to almost distributive lattice, we will define the set of all these ideals and filters. They form a bounded distributive lattice by defining the meet and join in these ideals as follows. If you see, if you see the join and meet in the set of ideals. So we have already seen that how the ideal will be in an ideal. And if the set of ideals, if you take, they are of the form, we are defining we are defining meet in the set of ideals as the intersection of any two ideals, and join of two ideals in an ideal of the form x join y, such that x is an element of the first ideal I, and the y is an element of second ideal j. With the help of this particular definition, we could see the psi join G is again an ideal in this in an almost distributive lattice. With the help of these two properties, we could see the set of all ideals in R forms a bounded distributive lattice where the singleton set containing 0, which is an ideal, acts as a 0 element of the bounded distributive lattice of the lattice I of R, and the greatest element of this particular set is nothing but the ideal R itself. And similarly, with the help of the definition of a filter, we could see if you define the meet and join in the set of filters as f meet G is equal to, it is similar to the meet of ideals, f intersection J, and
Excuse me, sir.
Yeah, madam.
Sir, screen is visible, very small size, sir.
Okay. Is this okay now, madam? Can you is it
Yes,
visible to
no,
you now?
sir, somewhat. Can we
Okay.
increase the size of the screen, sir? Murali?
Madam, is this okay now?
No, okay, sir.
Yeah, fine. The set I of R is having the all ideals of of our ideal almost distributive lattice, and those ideals by defining meet and join in such a way that I meet J is equal to I intersection J, and I join J is the set of all x join where the x is an element of I and y is an element of J. They form a distributive lattice, and of course it is a bounded distributive lattice, and the bounds are here 0 and the ideal R. And similar to the definition of this particular ideal, we have already defined a filter, and by defining meet and join in filters, you could see the definition here. And the meet of two filters is defined as the intersection of two filters, and join of two filters as the set of all x meet y, where x is an element of f and y is an element of g. And make sure that x meet y is not equal to y meet x. So in this case, we cannot write f join g is equal to g join f. After defining this particular property, we are able to see f join g is equal to g join f, as in the case of distributive lattice. So that is the advantage we are having in our almost distributive lattice. And mostly the purpose of introducing all these concepts is to get interest in the new scholars who are going to work in lattice theory, and particularly on algebra. And these are the properties we have. Whenever A meet B is an element of an ideal, we could see B meet A is an element of ideal only. But make sure that in almost distributive lattice, A meet B is not equal to B meet A. That means that meet commutative does not exist in an ideal, in any ideal R. And that is the advantage we have proved. Though with the help of those 5 properties we have taken as in the definition of a ideal, we could see in any ideal, whenever A meet B is an element of I, we can see B meet A is also an element of A. So see that if you observe each of these properties, whatever we have verified in an ideal, those are nothing but given in the definition of almost distributive lattice. Similar to that, if you see A join B is an element of a filter, we could see B join A is also an element of a filter. But make sure that they are not equal. And as in the case of distributive lattice, here also we have defined a principal ideal in a almost distributive lattice. See, the set is defined in such a way, the set of all A meet X such that X belongs to R. When you have these kind of elements, A meet X, and with a fixed element A in an ideal R, we could see that this forms a ideal. This particular ideal is known as a principal ideal. Similar to this, we can see we have done some operations on this ideal. And if you see, the join of two principal ideals is again a principal ideal, and the meet of two principal ideals is again an ideal. By defining this join and meet in similar way, we are able to find the set of all principal ideals. The set of all principal ideals, they form a distributive lattice, and this is, of course, they are all from the subsets of R, and they form a distributive lattice. We can see a distributive lattice is a subset of an ideal here. Similar to this, we tried to prove the set of all principal filters form a bounded distributive lattice, but we could not get. But because we need to verify the properties which are suitable for defining principal filters, the set of principal filters, will they form a distributive lattice due to lack of duality of join in meet. We could not see that the set of all principal filters, they form a distributive lattice, but we could see certain properties, and we have given a relation between a principal ideal and principal filters in this particular ideal. See, this is how we have given a different relation between a principal ideal and principal filter in an ideal. Whenever you take an element from an ideal generated by B, we could see that element is also element of the filter B because of these equivalent conditions. If you see these four properties we are having, they are equal, they are equivalent. So that is the relation between a principal ideal and a principal filter. And this is the most important definition we are providing here, relatively complement ideal. And this based on an interval defined in a almost distributive lattice. Whenever you have any two elements A, B in R with the condition A less than B, the interval AB is a complemented lattice. We all know this. And if R is a relatively complemented ideal, then every prime ideal becomes a maximal ideal in an ideal. Usually we don't have this particular property. Every prime ideal is a maximal ideal, even in our distributive lattices also. But if we have a relatively complemented ideal, in a relatively complemented ideal, we could see every ideal becomes a maximal ideal. And if you observe, as I already told you, the meet associative we have in ideals, but the join associative does not hold in ideal R. Throughout this discussion, but we are assuming the join associative because we need to, in developing certain concepts, we need to use this join associative. So we have considered join also exists. The join associative also exists in an ideal to develop certain number of concepts. And now, before coming to explain our normal almost distributive card, which takes a major role in developing relatively dually normal ideal. Now we are introduced a minimal primal ideals. We can find many of these properties on minimal primal ideals in my research paper. All minimal primal ideals in almost distributive lattice. Let us see how we have defined a minimal primal ideal in an almost distributive lattice. A proper ideal P of an ideal R is a prime ideal of R whenever X meet V, X meet Y in P, as in the case of distributive lattice, one of these elements, either X in P or Y in P, then we can say that the proper ideal P becomes a prime ideal. Similarly, we define a filter becomes a proper filter, a proper filter becomes a prime filter whenever we have X join Y in F, either X is in F or Y is in F. But these two properties made us to define another new concept which is known as minimal prime ideals in almost distributive lattice, made us to develop a normal almost distributive lattice. From then onwards, there is bulk of opportunities we got in developing relative annihilators, GLE relative annihilators, and the other properties known as GLE normal ideals and relatively dual normal ideals. In today's seminar or today's session, we are discussing these concepts. One is normal almost distributive lattice. Of course, we are not going to discuss more details on normal almost distributive lattice, and those are we are using certain aspects which are helpful for us in developing GLE normal ideal and relatively normal ideal and relatively dually normal ideals, and finally the concept of relatively dually normal ideals. So we are collecting only few of these properties, and if you see a relation between how we can give a relation between two ideals, and we have defined a homomorphism on two ideals. Let us see that particular definition here. If R and R1 are two ideals, and if we define a homomorphism, so if we define a function f from R1 to R2 by f of A join B is equal to f of A join f of B, and f of A meet B is equal to f of A meet B, f of A meet f of B, when we say that this function becomes a homomorphism on ideals and ideals. Now let's come to our major part, which is normal almost distributive lattice. Now, dear friend, the normal almost lattice was introduced long ago. In 1880, I could see a paper in 1880 developed by Dilworth. I could see the name almost distributive lattice. But I was wondered really to see in 1880, when the concept of distributive lattice was developed, we could see many aspects on only on distributive lattices have been developing, but we didn't see any generalization for a distributive lattice. But we, after developing the concept almost distributive lattice, we could see it's a generalization of many existing concepts of distributive lattices. So this made after some time we could see with I can insist this. After certain stage, instead of using distributive lattice, we can use an almost distributive lattice, because this particular distributive lattice will help us. This particular almost distributive lattice will help us in developing almost all properties of a distributive lattice. We can see normal lattices, which was introduced by Cornish in the year 1923, it seems. And basing on that particular paper, we tried ourselves whether we can generalize this type of normal lattice into an ideal with the help of an ideal. Yeah, luckily we got all the properties, whatever we find in a normal lattice, we could see those properties also hold in a normal distributive lattice. That made us, that encouraged those properties which we formed in developing a normal lattices, encouraged us to study more on normal almost distributive lattices, and see how he has defined the difference between the definition of a normal lattice and the normal almost distributive lattice. Let us see. Wow, Cornish has developed a normal lattice as a distributive lattice with zero, in which every primordial contains a unique minimal primordial. Just now we have discussed how we can define a minimal primordial, and we have seen some properties on minimal primordials. That means what? Even in almost distributive lattice also, we have minimal primordials. Minimal primordial, as in the case of normal lattice, we proved this result, this particular definition we proved in our normal almost distributive lattice after developing a concept which is known as the principal ideals. So before going to discuss about these principal ideas, I would like to give some annihilators. Let us see what is the annihilator. For any non-empty set S in R, if you take S star defined in such a way, this contains the set of elements of R satisfying the property A meet S is equal to 0. Then see, this is only a subset. It is a new form of a subset in a ADL. If you take in the place of capital S, if you take the capital S as a singleton set, then we will call this set as an annihilator of S in R, and we see some properties of annihilators in the following. Now let us see, whenever A less than or equal to B, the annihilator of B is a subset of annihilator of A, and if you see the annihilator A join B is equal to annihilator B join A. I already told you we don't have the commutativity and meet commutativity and join commutativity. So we can see we have proved this particular result. Annihilator A join annihilator B join A, and annihilator A mat B is equal to annihilator B meet A. But we are able to find the relation between while we are trying to define meet in annihilators, we got this relation A join B, annihilator A join B is equal to annihilator A intersection annihilator B. But we couldn't get this. For join annihilators, we didn't get that annihilator of A join B. But we could find only annihilator A join annihilator B is only a subset of annihilator A meet B. So because of this particular property, we could not develop this particular property 5. We could not develop the set of annihilator can form a distributive lattice. That we failed in that. But these annihilator will help us in developing a normal almost distributive lattice in such a way. In the following, we are going to see how it will be. And look at this property 8. If an ideal, the principal ideal A is a subset of the principal ideal B, we could see the annihilator B is a subset of annihilator A. Now, let's come to our main topic, normal ideal. See how we have defined normal ideal. Cornish has taken a normal lattice as it is a distributive lattice with 0, in which every primordial contains a unique minimal primordial. If you observe the definition of a normality in a distributive lattice and in a almost distributive lattice, now we could see an ideal R is normal if the is PI of R. That is the symbol we have given for the set of all principal ideals of ADL R is a normal lattice. Look at this. I repeat this because this is the definition we are going to use from every concept here onwards. From here onwards, we are using that normal definition in an ADL. An ADL R will be a normal ADL if the principal ideals of an ADL is a normal lattice. That means in the set of principal ideals of an ADL R, every prime ideal contains unique minimal prime ideal, as per the definition given by Cornish in his paper. And if you see this particular theorem, we have established the definition which Cornish has developed in his distributive lattice. That means an ideal R is normal if every prime ideal of R contains a unique minimal prime ideal. That means normality becomes a part of our ADL. So that we could define, we could generalize. You don't need any distribution. What you will have, you need the set of all principal ideals. If you have the set of all principal ideals in an ADL, with the help of those principal ideals, whenever in the set of principal ideals, a prime ideal contains a unique minimal prime ideal, we could see that ADL R becomes a normal ADL. So that is the definition we have given for a normal ADL. And we, from here in onwards, we could see all the properties, whatever we, in a normal distributive lattice hold, those also hold in our normal almost distributive lattice with a minimum number of conditions. And I already told you that I am not going to discuss all these properties here because we need to hurry to our main concept, relatively dually normal ADL. So these things, if any of you want to find these properties, we can find these properties, or many properties we could see those in my research paper, Almost Distributive Lattice, which was published in Southeast Asian Journal of Mathematics. Now, the duality. I already told you we don't have duality in an ADL. So we need to verify whatever property holds in an ideal, due to lack of duality in an ADL, we are supposed to verify those properties even in filters also. Usually we have an advantage. The dual of an ideal is nothing but a filter in a distributive lattice. Whereas in our ADLs, it will not happen because the duality does not exist in our ADL. That means what? The dual of a joint, if you take a joint semi-lattice, automatically, if you consider a lattice, the mid semi-lattice we can define. But such probability we don't have in our ADLs because we need to develop every property which is developed in an ideal cannot be developed in a filter. So we tried our best to do all the properties hold in filters. Luckily, all the properties of filters also satisfy the properties of ideals in an ideal. So my sincere advice to the young scientists who are working on lattice theory or in algebra, if you want to do some research work on lattice theory, you try to provide such type of definition. With the help of such definition, will we be able to find out or will you able to develop, as in the case of almost distributive lattices, can you see any duality between these ideals? Duality between the ideals and filters. That means if ideal we have, then is the dual of that ideal becomes a filter. If you are able to find such properties, if you are able to investigate, if you are able to find such type of definitions, we need not go for a almost distributive lattice. That definitions will help us to in developing almost all the properties of a normal, distributive lattice. And with the help of, see how we have defined a dually normal ideal. An ideal R should have maximum elements to become a dually normal ideal. When you have a maximal element, then only we can define a filter. So this is how we have seen in our earlier slides. If you see, if each prime filter contains a filter of this form, then we call that normal ideal as a dually normal ideal. And to develop or to introduce a dually normal ideal, we need to develop a certain type of annihilators. These are, we call these annihilators dual annihilators, because earlier we had, for developing a normal ideal, we have developed certain annihilators with respect to ideals, and we have seen those annihilators are ideals, and the dual to those annihilators, as we had defined here. Let us see how we have defined this. Let R be an ideal with maximum element, and F is any non-empty subset of R. This particular set, we didn't give any name for this. We didn't give any name for this, but we can call it as dual annihilator. The set of all X in R satisfying the condition S join X should be a maximum in R. R in the sense our ideal. That is, for every F, for every element of F, this element S join X should be a maximal element. So such type of elements, if we collect, they form a filter in an ideal. That filter, we are calling it as dual annihilator, and we'll see some properties on dual annihilators. If the set F is containing only a single element, then that set becomes what? See, S join X is a maximal element. So we have only one maximal element here. So corresponding to one in the sense corresponding to this particular element of R, X in R, we could see the maximal elements S join X1, S join X2, similar to those. If they become maximal, the set of all such maximal elements, see, and the maximal elements will come under one set, one set, but the elements which make to get those maximal elements will form an annihilator. That means a filter. So this is that. The lemma will tell you that for any X belongs to R, such elements we have seen earlier in the above definition, such duals form a filter in a ADLR. Now these are the properties we will see on dual annihilators. Whenever A less than or equal to B, we could see the dual annihilator A is a subset of dual annihilator B. But we don't find that in our idea. What you have seen there, if A is less than or equal to B, we have seen that the annihilator B is a subset of annihilator A. But when it comes to duality, particularly in our dual annihilators, the dual annihilator A is a subset of dual annihilator B. So completely, whatever property we proved in ideals, we need to do again, because the lack of duality in our ideal, we need to verify almost all the properties which we got in our ideal, which we got in the case of ideal. These are the things we can see. See, we can't form any distributive lattice because we don't have A join B. If you see the fifth one, annihilator A join, dual annihilator A join B, it contains dual annihilator A join dual annihilator B. We don't have equality there. If we have equality there, and because of with the help of the properties 4 and 5, we can form a distributive lattice. If you are able to find these two with the help of these two properties 4 and 5, if you observe, if we don't have this equality, if we have this equality, we can form another distributive lattice with the help of these dual annihilators. But somehow, because of the lack of that particular property, we could not get this equality. But so then we have taken them as some properties of dual annihilator to develop our next concepts. So see if such things happen, there won't be any difference between a distributive lattice and a almost distributive lattice. Only few such conditions we don't get in almost distributive lattice, except we have seen that meet distributivity, meet commutativity we don't have in ADL, meet join we don't have in ADL, join associative we don't have in ADL, absorptions we don't have in ADL. So though we are not having all these properties, we are able to find all the properties whatever we have in a distributive lattice in our almost distributive lattice. Really, it's a proud feeling for all of us who are working on almost distributive lattice. Still we are trying to find out the similar property which we have in distributive lattice are satisfying in almost distributive lattices are. So that's what I'm telling the young researchers. If you work on this almost distributive lattice, I hope by giving certain relaxation properties in the definition, you will able to find all the properties of distributive lattice. So that's why I have taken this paper for today's session to give this establishment will give you or will help you to work more on this type of developing this type of properties. They may help you in giving new concept, in giving with tremendous development ADL, not only ADL, it becomes a boost or generalizations for almost distributive lattice. Distributive lattice. GL normal ADL. Just now I told you that this definition, GL annihilator, helped us in defining GL normal ADL. Now let us see how we have defined this GL normal ADL. And from here onwards, so far we have discussed an ADL with 0. When it comes to duality, in defining dual annihilators and in defining dual normal ADL, we need to take an ADL with the maximal elements. Now let us see. An ADLR is a maximal with a maximal element is dually normal if for any prime filter F, the dual annihilator F plus is a prime filter. So this helps. If this dual annihilator becomes a prime filter of the prime filter F, then we will have a new concept known as dually normal ADL. Now we could see some properties here, and we can see the dually normal ADL properties also. Only I have collected some of these, and one of my research paper contains all the properties. They may help you in developing more concepts in ADLs. They may help you in some other way in generalizing certain aspects of distributive lattices. And let us see some characterizations here. if you take R is a dually normal ideal, see how we can given a relation between the dual annihilators x plus and y plus. These are all filters, right? The dual annihilator, the join of these two filters becomes our R. This is really a beautiful relation. While we are proving, see, after proving this one, we felt very happy. To be frank, this particular work gave tremendous satisfaction. This gave a lot of, I really satisfied a lot while after getting these results and all, because these are all preliminary results. If you see, if you are good in understand the definition of a set, and you will see, if you are sure about the definition of a set, you will understand how the elements of a set will act. You will understand the characteristics of that elements. So if you know each element, how it acts, you can see with the help of those elements, we can form different new concepts, and those concepts will help us in developing a new theory in our algebra. So these properties, you see, I have told you that in my earlier paper, the point, if you, I'll go back and I'll show you. Remember this particular three. We don't have this equality. We don't have this equality. Now look at this fifth property. We don't have this equality. The dual annihilator A plus and B plus is only a subset of the dual annihilator A join B. We don't have equality. I told you, right? We don't have that equality. But this equality exists here. Holds it. Let us see where it holds. Yeah, look at this theorem. If R is dually normal, if you observe the third property, you could see the equality holds. See that we don't get that equality. But if you consider this ideal is a dually normal ideal, then that subset, there we have only subset. It became what? Equality. Such a beautiful result it is. Such a beautiful result. And if you see this, the join of these two filters form occupies the complete area. Yeah, this is another characterization of dually normal ideal. See, the previous one is with respect to dual annihilators, and this is with respect to maximal, in terms of maximal elements. I already told you right throughout this particular session. In discussing this dually normal ideal, we consider an ideal with maximal elements. So let us see how we have defined this and how we have got this relation. If x comma y are elements of R and x join y is a maximal element in R, exist elements of the form x1, y1 in R satisfying this condition, x join x1, y join y1 are maximal. And x1 meet y1 is equal to 0, then the ideal becomes a dually normal ideal. So this is another important result we have. There are many characterizations we could see now. We are going to see also. If you have a normal ideal, we have introduced a duality to that normal ideal with the help of dual annihilators. And a dual annihilator, of course, it is a filter we have shown, and the set ideal, since it contains maximal elements, we have got a dually normalized with the help of that dual annihilators, and with maximal elements we have this relation x join x1, y join y1 are maximal, and satisfying this condition x1 meet y1 equal to 0. We could see these maximal elements, they form with these conditions, they form a dually normal ADL. This is related to maximal elements. That's what I'm telling. If you are sure with the elements how they act, we can give, or we can introduce many such interesting concepts. Now let's come to our relative annihilators. So far we have discussed annihilators, dual annihilators, and this is relative annihilators. Let us see how we have defined relative annihilators. R is an ADL, and A is any non-empty subset of R. If we take, now fix an element X in R, we define X meet A. These elements of the form X meet A, where A is any element of A. Now, look at this. It is just a set now. Let us see how this set will act in the next slide. But before that, we should understand how we have defined the relation between. We gave a relation between an element and a set, and it is defined the set of all X meet A, and every the elements of A are involved. And we gave a new set here. We'll give a new name to that. We haven't given any name to that because we are going to discuss what is known as a relative normal ADLs, right? Yeah, this is the set AB is equal to, we are selecting elements of R such that X meet A is an element of capital B. So this X meet A in 1, whatever we have to, such elements are in B. They are of this form. They are of this form AB. This is the notation we have. Because why I am insisting in this definition? Because this is the definition we are going to repeat till the completion of this particular chapter. We are going to repeat this particular definition. See, look at this definition. Once again, I repeat. X meet A is a subset of B. This is how we have defined. These are the properties. And remember, these are only sets I have taken. Just A, B, C are any sets in an ADL. And whenever we have A is a subset of B, the set CA is a subset of CB. Similarly, A is a subset of B implies we'll get BC. That means whenever E have such relation and C is any non-empty set of an ADLR, we have these relations, right? Now, you may ask, this is comes under, see, we have studied about many things in introduction on the union of sets and all, in set theory. But of course, everybody knows that the set of all subsets of a particular set, the power set of a particular set, they form a distributive lattice, right? And this is the base for any of us algebra when you want to discuss something, some concepts in a lattice theory and lattices, you need to know all the properties of those set theoretical notations, of course, those relations. And this is a particular relation we have defined here between these sets. And these sets, these particular sets, and we are going to, in our coming discussion, we are going to show they become ideals. They become ideals. And let us see when they form, when they become ideal. When that set AB or CB, whatever you have taken here, when they become an ideal. Let us see here. Yes. This is that. Actually, this is only, I already told you, right? This is only a set. This set becomes an ideal with certain condition. When it becomes an ideal, we'll prove it later. I gave an example also here. If you see, I think, okay, fine. If you, I had taken ADL, R is equal to the set 0, A, B, C. As usual, I told you that with these 4 elements, this set R forms a almost distributive lattice by defining join and meet in such a way. The tables we had given for this composition table I have given for the join and meet. And if you see, by defining in this way, the set becomes a ADL with 0. The set becomes a ADL with 0. Now, you choose A is equal to set containing AB and B is equal to set containing 0, AB. You need a table, right? They are just subsets of R. And after defining these two, AB, after selecting AB in such a way, if you see B meets C, look at this. B meets C, you have C. That means B and C are their elements, but it is not an element of B. But as per the definition of our ideal, if B is an ideal, when it meets with any element of R, that result should be in the ideal. So it is clear that because B is in B and B meets C is equal to C is not in B, it shows that the set B is not an ideal. It is just a set. So we have taken only sets A and B. And let us see, therefore what you have? B is not an ideal. But what you have, as per our definition, A meet A is a subset of B. We will get this set, 0 AB. But what did you get? This 0 AB and B equal to 0 AB both are equal. Therefore, what did you get? AB is equal to B. AB equal to B implies what? This is not an ideal because B, we are clear. It is clear that B is not ideal. This set AB is also not an ideal. That means what? It is simply a set only. It is simply a set, not an ideal. Now, when this particular set becomes an ideal, let us see here. If B is an ideal in the set AB, if B is an ideal, then the set becomes an ideal. Really, see, by giving by changing the sets, what happens if A is an ideal? What happens if A is a filter? What happens if A is equal to 0? A singleton set containing 0. If you think in such a way, you will get more number of properties. Of course, we have done those things in our in the next slides and all. See, if you take B is an ideal, the set AB, so far what you have taken, it is only a set, becomes an ideal. Now, this ideal made us to introduce a relative annihilator. I gave an annihilator, dual annihilator, and so with those, now we are giving. They are different. Each is different, right? Each is different. Now we are giving a new concept which is known as a relative annihilator by taking B as an ideal of R. So this is, we call this ideal as a relative annihilator of A with respect to B, because we need B. B is the ideal there. So I already told you, if you change the roles of A and B, take A equal to something, B equal to something, if you change, then what happens? You see, if you change B is equal to, we know the set singleton set containing 0 is always an ideal. If you take B is equal to 0, as per our discussion and as per our the example and all and the theorem, we could see this set is a ideal, and this ideal becomes an annihilator of A. B is equal to 0, we call this as annihilator A. Let us see how it will be. Let's see how it will be. Yes. Yeah. And, yeah, right. If B is an ideal, we have that B itself becomes a subset of this ideal AB, because we have taken B as an ideal, right? This B, whatever you have taken in developing this particular relative annihilator, this ideal became a subset of the relative annihilator AB. This is for any subset you take, for any subset A. If A is equal to 0, see, the entire ideal becomes the entire ideal R. That's what I told you, right? You change the roles of A and B. In that set, if we have an ideal in the place of B, we are getting a relative annihilator. If we change in the place of A as the singleton set containing 0, we are getting the entire R that occupies, that ideal occupies the entire R. Now look at the third one. B is an ideal and AC are any two sets. And if you have A is a subset of C, then the ideal A CB is equal to AB. See that? And is equal to C comma ideal AB. Right? This is how we can define, by changing or by giving relations in the first place of a subset. Now these are the things we have developed. B is an ideal of an ideal R. Yes, A is just a subset. Then this ideal AB is nothing but is same as this ideal A comma ideal AB. Look at this. This is really interesting. If you see, this is really an interesting result. That means what? Now, from here onwards, what we are doing, in the place of sets, if you take singleton, the sets with single elements, singleton sets, if you take, what happens? Now look at this. In the place of A, if I take a single set containing A, then we get these two ideals are equal, where the first place is what? We are already discussed about that this is the principal ideal. This is the principal ideal generated by the element A in an ideal. Element to a set, the ideal, the dual annihilator AB is nothing but the set principal ideal generated by A and the ideal B. And let us see what happens if B is also equal to a singleton set. Now you may have a doubt. Is there any chance for us to replace the set B by single element? What happens? If it is a single element set B, let us say it is a B, since the single element set B is not a ideal, we cannot consider it into as the entire set cannot be considered into an ideal. So there we have a bit confusion. We have discussed it that if B is an ideal, only then this set becomes this dual becomes a this relative annihilator becomes an ideal. How can you change the place of B with a single element? Now, the beauty comes here. See this? As in the case of this particular property 5, now look at this 6, how it has changed. We know that the capital B, in the place of capital B, had taken the principal ideal generated by B. We know that this is a ideal. And this is same as, because capital B place, see, we had taken this is ideal generated B. Since it is an ideal, if you replace this in the place of this set AB in the property 5, this is nothing but the ideal generated by A and the ideal generated B. And this is equivalent to, see this is equivalent to the set AB. This gives another concept, new concept. By changing, just that's what I told you, by giving different, by testing the elements of the sets A and the elements of the set B, we will have different new sets. This is a new set, AB. We are not sure what is AB here, because what you have discussed, if B in the second place in the set AB, in the second place if you have B as an ideal, then only you will have this set becomes an ideal. But we are not sure what it is. But we have shown that, look at this important note, we have shown that these two are equal. These two sets are equal. And this, observe that you have written here, right? This helped us in proving this. The note, observe that whatever I have taken here, this helped us in proving these two sets are equal. Now look at this. If these two sets are equal, since on the right hand side set, if you have the set generated by B, and this is a principal ideal generated by B, that means it is an ideal. The right hand side set is an ideal. Since these two are equal, then my left hand side set now become a new ideal. I could form that. Therefore, what do you get? If B is an ideal, see, that's what I have written here. Since the principal ideal B is an ideal, the set generated by A, ideal generated by A, and the ideal generated by B becomes an ideal. And hence, my left hand side set AB becomes an ideal. What a beautiful theorem it is, right? We didn't get, we don't, on right hand side, we don't have any ideal. In this new set, we didn't use any sets here. Now, by introducing a new set like X meet A is equal to, so that's what that's why I repeated there many number of times. You might understand, right? Why I repeated that particular definition many number of times. Why? That is only set I have taken there. That set, if I change the second place with the different sets, and at some time I changed it as an ideal, that set became an ideal. And we are already proved that if that set is not an ideal, that particular set, a relative set, cannot be an ideal. It is only a set. But later on, what happens? After changing the nature of the sets, by taking singleton elements, by taking what are known as principal ideals, we got this, finally got this particular result. Now let us see what we have got with this particular result. Now we can observe the following. If AB are any two elements of R, then C, this forms an ideal for us. That means what? Whatever element you take, if you define a set in this way, you will be getting collection of sets of, number of ideals. You choose some of them, you try to see or verify I try to investigate what type of properties we can have with such type of ideas. We don't need any sets and all, right? We don't need any definition also here. We need only one definition, which is nothing but what is the set, AB. If you know that particular set, how we have defined for any two elements, if you take from an ADL, we can form ideals. Now let us see what happens if A is having certain 0. A is equal to a maximal element. If B is equal to 0 and B is a maximal element, if we change the nature of that particular element in a different way, you will get different properties. Let us see here. For the second one, yeah, this is okay, right? Now these are the relations we have. These results will help us in developing the dual normal ideal. Some more observations. That's what I told you, right? Luckily, actually these two sets are not equal. But when these two sets are equal in the lemma, if you see the first one, if you observe the first one, what you could understand? Whenever A meet B is equal to B and B meet A is equal to A. That means I'll come to that. We have in the initial stage I have given. Yeah, madam, can you hear me? Hello?
Yes, sir.
Yeah, is that okay?
Yes, sir.
Yeah, fine. Okay. Now let us see. We have seen that by defining less than or equal to in an ADL, that ADL forms a partial ordered set. That means what? If we have A less than or equal to B, since it is a partial ordered set, if A less than or equal to B, instead of this particular property, in the first property in this lemma, if you see, if A less than or equal to B, what you will get? A meet B is equal to A. So in such a way, we have defined meet and join there with the help of the partial ordering less than or equal to. Right? Now, if A meet B is equal to B, remember, we don't have the commutativity. A meet B is not equal to B meet A. We are supposed to remember that because see, if you take A meet B is equal to B meet A, what happens? A equal to B. If A equal to B, there is, let us see what happens. That will become a confined to a single set. Let's come to that later. Now, before this, if you take A meet B equal to B and B meet A equal to A, we are sure that A meet B is not equal to B meet A. Therefore, A is not equal to B. Whenever A is not equal to B, and you will have C, AB is equal to the ideal. AB is equal to the ideal BA. See, in each case, X not equal to, if you take X not equal to Y, if you take, what happens? The ideal XY is equal to ideal YX. That means you will be having different ideals you will be having by changing the nature of the elements of that particular set. Now look at this. I told you, right? Already I informed you about this particular thing. If you take B is equal to the least element of an ADL, the 0 element of an ADLR, A0 is equal to what? 0. When you have A is equal to 0. We have A equal to 0. Now, similar, these are all such type of results you are having. We have seen by observing in the places A and B, if I replace different elements, what happens? So this is how, if I replace by A meet B, or similarly, you can see these things we can verify later, no problem. We are almost close to our last topic, and these are results. See, A meet B, these are all equivalent. B meet A. If I replace A by A join B, that is also equivalent to this particular sets. See the interesting things by changing the places. B join A. Actually, we don't have A join B, B join A, but we have this condition. In the case of this relative annihilators, we got these properties. A join B, A meet B. These are all, and at the same time, these are all equivalent. Now, A, B, if we, by changing the different elements with the help of A and B, A meet B, A join B, B join A meet B, B meet A, by changing in each place, first place and second place, you will be having all those. And if you see, if the first place is replaced by the least element of this ADLR, we will be getting R. I told you, right? If both the elements are equal, what happens? If both the elements are equal, AA, you will be getting the entire ADLR. See this. Though they may look similar, 2 and 3, but here they are completely different. They are completely different. Now, some more properties we have here. I already told you, right? In the first place, if we have A join B, and this is similar to the equal to the ideal B join A. See, A meet B, B meet A. And if in the second place we meet A meet B, B meet A, and we don't get any A join B, we got A join B also here. But see, we didn't get this equality. You know what happens? What happens if you think it in a positive way? In the other way, someone can work on that. Someone can work on that. In this fifth condition, fifth result, in 1 and 2, we have less than or equal to. Sorry, they are contained in the sets. What happens if they are equal? That means what? The join of two ideals becomes an ideal. Again, the join of these two ideals is again a subset of this B join C. So we could not give that relation, but you will be getting that when it happens. So now let us see in this one. If R is a relatively complemented ideal, then we'll have AB join AC is equal to A B join C. Really wonderful. We have explained when an ideal becomes a relatively complemented ideal. Relatively complemented ideal means what? Whatever interval you have taken there, that interval becomes a distributive lattice, and which in terms we call that if it is a complemented ideal, that becomes, that means that interval in that ideal becomes a relatively complemented ideal. If that interval is an ideal, right? Yeah. Now look at this. I told you, right? If we place this one by 0, we will get a annihilator. And what is this? Just we are recollecting those. It is the annihilator is defined in where the set of all x which are having this relation A meet x equal to 0. We collected those and we have proved this is an ideal. And similarly, A join B or B join E is an element of this particular set. If one of these, an element of this particular ideal, then that ideal becomes R. If A meet B is equal to 0, and for any C belongs to A belongs to BC. If you just replace those elements and see what type of relation you will be getting, right? Now, by using these are all different properties we are having, right? Different. See, these are all preliminaries. We need to work hard by giving, by replacing. That's why I told you, for freshers who are going to interested in doing research work and all, the only thing what you need to do is we should understand the nature of the elements of the set. If you are sure about the nature of each of the elements of a set, you can play with them. You can create wonders. We have not given any, see, these are all different, based on elements. Randomly we are choosing. Take A, take B. What happens if A is a maximal element? What happens if A is a zero element? What happens in the place of A if you replace A meet B? What happens if you have A join B? Of course, at the same time, you need to verify B meet A also, because we don't have the duality, right? We don't have the duality. This is how we can develop a new concept. Everybody can do who are interested in doing some work, want to introduce a new concept. So that is, this made me, this particular idea made me to introduce, to take in today's seminar. That's why I taken this particular concept. And these are the basic things, whatever you have taken study here, they basic, just replacing. What happens if you, in the place of A, if you keep the B, an ideal, if you place an ideal or a filter, if you take in that place, if you take R, what happens? The idea in thinking, I mean, in a different way of thinking, the different way of thinking will get a new concept. That new concept, if you study in a, if you study deeply, there is an opportunity for us to create more and more and more and more results, right? Now, so they are similar to that. But this particular fourth property is important for us because we are going to use this particular result in our coming slide. Now look at this. Now comparable. You might have heard about comparable. So far we haven't discussed comparable. But if any two elements are comparable in that partial outlet set, that becomes a distributive lattice. We have discussed it, right? It forms a chain. But we don't want to be frank, I'm telling, I don't want to put the name distributive lattice here. Why? This ADL definition is enough for me. This ADL is enough for me to grab all the results of a distributive lattice here. Then why do you need an ADL? How many properties it has? It has to, it is mid-semi lattice, it is joint semi-lattice. The inclusion of all these properties, distributive properties, absorption properties we are having. There are 4 absorption properties we are having, 4 distributive properties we are having. And you need mid-semi lattice, you need joint semi-lattice. How many properties you have in a distributive lattice? But here you have only how many properties? Just 5 properties we have. With less number of properties, we are abstracting, trying to give all the results of a distributive lattice. Now we can see which is the advantage for us. Which is the advantage for us. So this made us develop all this. Do you have any doubt regarding this? Want to speak to me? Fine. I could hear some voice from your side. Yeah, this is the characterization of a ADL in terms of relative annulator. What we have discussed so far. R is a normal ADL. When we have, these are all equivalent. If R is a normal ADL, these things will hold. The ideal AB join BA is equal to R. And with the condition A mid B equal to 0 is important for us. And whenever you have A mid B equal to 0 and F is a filter, you will have this A mid X and B mid X are comparable. Comparable in the sense we have that ordering. In what way we can compare? The ordering we have less than or equal to. That means what? Either A mid X is less than or equal to B mid X, or B mid X is less than or equal to A mid X. One of these conditions will hold. Now, this is our relatively normal. This is how we have defined a relatively normal ADL. With the help of those relative annihilators, we have discussed this. We have introduced this. The sectional normal annihilator will move on to, I will move on to our main topic. Relatively complemented ideal I have discussed earlier. Now, see, this is the relation. If R is a normal ADL, if R is a normal ADL, for any ideal not equal to R, is a normal as a subideal of R. Whenever you have considered it as a normal ideal, you have these equivalent conditions. Those three are equal now. Now we have a dual to that. Dual to that relative annihilators we have defined earlier. We defined a new one here. This is what X mid S is equal to A in this interval. These are the things. Let's move on to our topic. These are all, see, these are all the relations. If R is a relatively normal ADL, then we'll have AB join BA is equal to R. A mid BC is equal to AC join B. I told you, right? We'll be using this particular thing here. And these are the equivalent conditions on relative normal ADLs. If R is a relative normal, these things will hold. If any of these, one of these hold, then that becomes a relatively normal ADL. This is another result based on those relative annihilators. Yeah, these are all such some of those. See how many, you can see how many results we have established. These are all. Yes. Let's come to our homomorphism. Basing on homomorphism, we have proved all these. Now, one second. Yeah. So this is the last concept we are going to. With this, we'll close this session. Now, see, look at this, the slide. If you observe this slide, what do you have? From the definition of an ideal, we could see, we have seen that this distributivity hold, A join B meet C is equal to A meet C join B meet C. But we don't have this particular. Second one, A meet B join C is equal to A join C meet B join C. We don't have. That means what? The duality, here we have C, meet C, we have join C. If we have meet, we have this result in ADL. If you have join, this won't satisfy in ADL. That means the meet and join, they are not dual to each other. They are not dual to each other. So this made us, as we have discussed in earlier classes, in ideals and filters, here also we are discussing, or we are giving some definition. There we have defined A meet X, right? Now we are using what? A join X. And these are dual to those which I have studied earlier. We are getting. And similar to that, if you see these results. These are the results with the help of those definitions we will be having. These are the proofs and all, of course. You can get all these results from my research paper. If any of you need it, I'll provide that information to you to go through those results. This is real generator. See, if A is a filter, then A equal to R the set. If B is a filter, AB is equal to R we are getting. These are the results we have. Those things we need now. We don't have equality. We don't have certain properties. So this is, we have only subsets we are having. That means what? We don't have equality. But when it comes to define a new concept, we are considering that as if it exists, what happens, right? Let's see that. Yeah, look at these results. Similar to those annihilators, relatively dual annihilator, we got all these results. You can see all this. Yes. Look at this. The frame also is in a beautiful way we got. Yes, this is our top. Now let's finish it in 5 minutes. So this is the definition we have gave. Relatively dually normal, right? If AB is dually normal, then we call interval. The interval AB is dually normal. Then we consider, and then we have defined this R is a relatively dual normal. And these are the definitions we used in our, in the earlier classes. With that, let us see what we are getting. Yeah, this is important for us. This result will help us a lot, improving many results. Whenever in the interval it is clear that A is less than B. Whenever you take elements of this interval, then you will have this. This is really a beautiful result. If you see this, you may not understand by studying all this because we don't have, if it is if those things are with you, you will understand how we have developed these concepts and all. But those things you have explained how we have developed these and what are the definitions you have given for this. Let's come to the topic. These are all based on nature of the elements only. We have got all these. Look at this. Relatively dual in normal.
అది లంచ్ బ్రేక్ లో ఇవ్వమన్నారు కదా, ఇప్పుడు కాదు. లెటర్ లంచ్ బ్రేక్ లో కౌంటర్ నంబర్ 5 లో మీరు లెటర్ రాసి.
Is that okay? Okay, right. So these are the results we have. If R is relatively dually normal, there we have proved if R is dually normal, ideal AB join BA is equal to R. But in the here, if you observe, R is relatively dually normal, then R is equal to, these are all filters, right? We have discussed it, right? I have shown. AB join BA for all AB belong to R, and similar. These two are equal. We don't have that equality I have shown. In terms of elements, we are getting a beautiful results for relatively dually normal ideals, and we don't. I don't want to discuss more on this proof and all. So this finally, let's see what are the how many results we got on these relatively dually normal ideals. Yes, this interval is dually normal. Whenever it is, we'll be having a relatively dually normal. And yes, see, this is what with elements only. If you understand whatever we have observed, if you see, those are the three topics. Three concepts we have defined. One is ADL. It is it's so simple as of with property five properties, and yeah. See, this is the slide. Almost distributive lattice, and when a normal almost distributive lattice becomes a normal almost distributive lattice, and after the our topic is this: how we can convert an normal almost distributive lattice into a dual normal ideal, and on that we have defined some relative annihilators. With the help of those relative annihilators, we have defined a relatively normal ideal, and dual to that relative annihilators, we have defined dual annihilators. We have defined relatively dual annihilators, and with those annihilators, we have defined a relatively dually normal ideals. Thank you so much to the management of JMJ College, Tenali. Thank you so much, madam, for giving me this opportunity. Because I am interested in this subject, I would like to express such type of relations, how we can use the elements of a set. If you are sure the nature of the elements, the young researchers are the researchers will able to develop many things.
Yes, sir.
Yeah. So there is a just by knowing the nature of the elements, we can create many such opportunities. We could see the Boolean algebra helped us in developing computers, and there are many developments we are having. There are many developments we are having, but ours is as a pure mathematician. Yes. My intention is to give the idea to the students, how we can see, how we can develop, in what way. The only thing is, if whatever you set you find on a table or a book, wherever it is a school student's book, it doesn't matter to us. The only thing is, whatever set you have, you try to find how we can utilize the nature of those elements. That will help us in creating new concepts and wonders we can create.
Yes,
My
sir.
intention is that with that intention only I could see what are the how we could develop all those sets, how they helped us in developing new concepts known as dually normal ideal, relatively dually normal ideal, and those are all the things we have seen in that.
Yes, sir.
I took much time of you. Any of you want to raise any questions, you can ask me.
Okay. Thank you very much, Professor Ravi Kumar, sir, for enlightening us and stimulating with a stimulating speech. Your presentation has an excellent content on almost distributive lattices and its normal, dual, and relatively normal concepts, which are very relevant to this recent research. Your talk was insightful and refreshingly and stringent and very much interesting in learning of annihilators in ADL, dual annihilators, and some properties of various annihilators. Thank you very much, sir, for giving a nice presentation on ADLs and recent advances in ADLs. Now, for the next 10 minutes, question and answer session. Sir is ready for asking questions. If anybody having doubts, please unmute your mobile and ask the resource person in microphone or post a query in the chat box. It's a benefiting platform to stimulate and enhance our understanding of topic by exploring our doubts and questions. May I now request the participants of the FDP to interact on today's session on normal ADLs and relatively dually normal ADLs, and sir is ready to answer your questions.
I think they are not interested. It's okay.
Sir,
They can
sir,
find if they
sir,
madam
there is a
provide
question
my
for-
number to them or my mail ID to them. If anyone wants to contact me, they can.
Sir, there is a question in the chat box, sir.
Yeah, madam.
And Dr. Panindra Kumar sir posed this question.
Yeah, fine.
Can we induce pseudo-complemented lattices in ADLs?
Yeah, of
I
course,
repeat,
it's
sir.
already done. Yeah, Dr. Panindra. Yeah, that work is already done by Professor Nanaji, who is a
Okay.
colleague of mine. You can see if any of you interested to find out the topics what I have done so far.
Sir,
I know Fanindra is close to me. You can come here at any time. I'll provide all the information, whatever you need of. Already pseudo complementation is introduced.
thank you very much, sir. Are there any other questions? No one has any questions, sir. So there are no questions, sir. So once again, thank you very much. Now I request Ms. Bharati Madam to propose vote of thanks.
Thank you. Thank you is such a word of gratitude that cannot be seen or touched. It must be felt by heart. I feel honored and privileged to propose a vote of thanks on this special occasion. Dear participants, I would like to thank our resource person, Captain Dr. S. Ravi Kumar sir, for his active participation in FDP. Sir, you truly made this day full of knowledge for us on ADLs. Your deep intellectual way of imparting knowledge on principal ADLs, filters, and normal ADLs in terms of its prime and minimal prime ADLs in an ADLs. Today we have got a lot of information on the concept of annihilators, dual annihilators, and relatively dual annihilators and their properties in an ADL. These type of lectures are very useful for young researchers, sir. Once again, thank you, sir, for sharing your expertise lecture with us and enlightening us in spite of your hectic schedule. I convey my deep regards and heartfelt thanks to our correspondent, Dr. Sister Teresa Gade, for her support. My sincere thanks to Dr. Sister Shaini KP, principal of our college, for her help and support at various steps. A special thanks to the convener of this 5-day national level online FDP, Dr. S. Uma Maheswari, the head of the Department of Mathematics, and organizing secretary, Mrs. C.M. Manita, the head of the Department of Physics, for making today's session a grand success. My deep sense of thanks and appreciation to all the participants who actively participated in this FDP. Last but surely not the least, let me thank Mr. Murali and Mr. Ravi for their technical support. Once again, thank you all for being with this afternoon. Have a wonderful day ahead.
Thank you so much, Professor Ravi Kumar sir.
Thank you so much, madam. Thanks to the entire organization, you are doing very good job. And I hope our session will helpful for some of our young scholars.
Yes, yes.
Thank you so much, madam.
Thank you, sir. Thank you. Thank you, participants. Thank you so much. Now we close the today's session. Close this, everyone.